Thanks for the introduction. My name is Takemi Nakamura, and I'm now a PhD student at Nagoya University in Japan. First of all, I would like to thank to the organizer for having me here. And now, I'm going to start with the. This is the simple overview of my talk. And firstly, the background. I'm going to start with a few things about information geometry in equilibrium statistical mechanics. According to standard statistical mechanics, if a physical system with a Hamiltonian, H, is in its equilibrium, the system can be described by the Gibbs distribution, and which is written in this form, and this probability can be rewritten in this form of an exponential family. So we can regard a parametric family of Gibbs distribution for a Hamiltonian as an exponential family. And here, beta is the inverse temperature, and the z is called the partition function, and theta represents the canonical parameters and forms a coordinate system, and the set of y represent classical, meaning commutative physical quantities such as magnetization as random variables. And the last, the psi, is given by the logarithm of the partition function and is called the potential function, or massive potential in thermodynamics. And next.
The green.
Yeah. Okay. And so we have manifolds, so we can introduce the official metric on this family, and consequently, the metric is the Hessian of a potential like this, and this metric is equivalent to the so-called Rupana metric through the Legendre transformation, and which is given by the Hessian of entropy. Okay, and so now we have a metric, so we can calculate the scalar curvature. And what is important here is that scalar curvature of the exponential family is physically significant, and is meaning more than just a geometric quantity. And for example, the scalar curvature is related to the correlation volume, or the correlation length C of a thermodynamical system with a spatial dimension of D. Yes, and also it's the sign of a scalar curvature is physical meaning. The scalar curvature is related to the system being attractive or repulsive as a whole system through its sign. And here, if we define the curvature as negative for the sphere, then if the scalar curvature is positive, it's going to be the system tends to be repulsive. And on the other hand, the scalar curvature is negative, then the system tends to be attractive. And the border is vanish when the case of vanishing scalar curvature, and the system is considered to be non-interacting. So
you can use.
Okay. And so so next I'm going to talk about the motivation. I have discussed classical context so far, and from now on, I move on to the case where the quantumness is required. And so we have seen that the classical scalar curvature is physically significant, but the what about quantum scalar curvature? I mean, how physically significant is the quantum scalar curvature? And this is not studied so much, as far as I know. And especially, I'm curious to find out how the quantumness can affect the scalar curvature, and what kind of physical information we can extract from the scalar curvature. I have motivation from mathematics as well, and it is related with the so-called Petz conjecture. And the conjecture is about the monotonicity of the scalar curvature. And roughly, and partly physically speaking, the conjecture states that the scalar curvature of the space of all invertible states and not a parametric subfamily equipped with the Bogoliubov-Kubo-Mori metric is conjectured to be a monotonically decreasing function of the temperature. And the conjecture has been proven to be true in the 2x2 matrices case, two-level system. And my question is, how about the monotonicity of a parametric subfamily, especially of a physically interesting parametric subfamily, like the Gibbs state plays a central role in quantum statistical mechanics, and in physics, the number of parameters in Hamiltonian are at most a few. So my question to address is whether the scalar curvature of the quantum exponential family for a specific Hamiltonian is monotone with respect to the temperature or not. So with these motivations, I have in the study, I have picked up transverse-field Ising chains as a specific Hamiltonian for Gibbs states, and study the temperature dependence of the scalar curvatures in the chain size, in the various chain sizes of n equal 1, and which is the non-interacting system case in the 2, 3, and infinity. And before presenting the results, I move on to preliminaries to explain some notions in mathematics in more detail. First, about the Gibbs state and the quantum counterpart version of the Gibbs distribution. And in quantum mechanics, the Hamiltonian becomes an operator acting on Hilbert space. And in this case, the Gibbs state is a mixed state written in this form, and as in the classical case, it can be written in this form. So this belongs to the quantum exponential family in this way. And most things are in here in common with the classical case, but the one distinguished difference from classical case is that the physical observables all are generally non-commutative. I mean, if they otherwise these physical they can be simultaneously diagonalized, and the situation can be reduced to the classical context. And so, yep. And next we consider metrics. What is the difference from the classical case is, with regard to metric, is that there's no unique monotone metric in the quantum context, and so here we introduce a Riemannian metric onto the quantum exponential family by means of the quantum relative entropy, defined as this, as a distant light measure. Sorry?
Closer to the microphone.
Yeah, so specifically a metric is given by the distance between neighboring parametric states, like this in the consequently this Jij corresponds to the Hessian of a potential function, and thus as you notice that this form is exactly the same form as the fish metric in the classical case. And this metric is called the Bogoliubov-Kubo-Mori metric, or the canonical correlation in linear response theory. Yeah, we have metrics, so we only curvatures. We can introduce Christopherson relativity connection by this equation, thanks to the Hessian metric, and therefore we can obtain the Riemannian curvature tensors like this equation. And yeah, and here I'd like you to keep in mind that the curvature of the sphere becomes negative by this definition. And yeah, I'm going to touch on a little on the transverse-field Ising chains. The Hamiltonian of the n-spin transverse-field Ising chain is given by this, and the with Pauli matrix is defined as follows. And there are mainly two terms, and one is the spin-spin interaction, and the other comes from the transverse field. And so there are two parameters here, theta 1 and theta 2. And for the rest, we will set J equal 1 as an energy scale and consider a ferromagnetic interaction in ferromagnetic cases only. And yes, and we also impose a periodic boundary conditions for n equals 3 or more. And what is important in this Hamiltonian is the quantumness that comes from the non-commutativity between the Pauli matrices. And so sorry. What? Yeah, I'm going to resolve. Our first case, in the thermodynamic limit, the temperature dependence of the scalar curvature is on the right side with semi-log plot for y-axis, and as you can see, the scalar curvature is monotonically decreasing, and also it can be positive. It's positive, and these properties seem to be independent of the strength of the transverse field, but the one except for the quantum phase transition point, it seems that the scalar curvature is following the power law, and so we have a piece of information on quantum phase transition here. So in infinite size, the monotonicity seems fine, but how about finite sizes? And the answer for n equal 2 is, you can see that scalar curvature is apparently non-monotone with respect to the temperature for a specific value of transverse field, and it can have negative values for particular values combinations of transfer field and temperature, for example, around here. And yeah, let me show you the case of n equals 3. And yes, also in this case, no monotonicity and negativity appear. So so how can I say it? If the transfer field is sufficiently large against the interaction strength, the monotonicity seems to recover. Yep. So lastly, so far finite size effects seems to appear. So lastly, how about finite size but without interactions? Oops. What? Oh, sorry. So to consider the case, I will introduce the no-interaction chain defined by this Hamiltonian, and for this Hamiltonian, the scalar curvature apparently monotone and positive, so monotonicity and positivity come back in this case. And these properties won't change so much if we change transverse field. So let me conclude my presentation. Yeah. So in this study, I studied the monotonicity of the scalar curvature of the quantum exponential family for transverse field Ising chains in n equal 1, the sizes of n 1, 2, 3, and infinity. And as a result, I find that if a chain is either infinite size or non-interacting, the corresponding scalar curvature is monotone and positive. These two properties are quite similar to that of the thermodynamic entropy, so I'm wondering whether there is any relation. And on the other hand, if a chain is in finite size and interacting, the scalar curvature can be non-monotone. And furthermore, it can have negative values for particular values of transverse field and the temperature. So from these observations, I think that the balance between ferromagnetic interactions and quantumness that comes from non-commutativity between observables determines the behavior of the scalar curvature. So that's all for my presentation. Thanks for your attention.
So thanks for the presentation. Is there any question? Okay, so I have one question. So first of all, what do you think will happen if you had 3 interaction between 3 objects instead of 2 spins? Do you think that the description will change a lot if you consider 3-point interaction instead of pairs?
3-point interaction.
Yeah, within 3 spin. Yeah.
3-point interactions. I understand.
Also changing is adding more
High terms.
Yeah.
Honestly, I'm not sure.
You have no idea.
I have no idea. Yeah, I have never tried it before, okay. So I'm sorry. I have no answer to tell. Tell you.
And do you think there is some connection between your behavior and some universality class that you can find in the transition you were describing?
Yes,
some universality idea?
Universality class?
Yeah.
You mean the
in the infinite this
Yeah.
case?
This one.
Mhm.
Yeah. I don't know what.
You've studied the
What-
correlations or something like this? Have you studied correlations and connection between correlations and this behavior of the curvature? No, or not?
Sorry.
Have you studied the connection between correlations and this curvature and the behavior of the curvature?
Yeah. I'm sorry. I don't study that connection, and I will try it in the future.
Okay, so thanks again the speaker, and let's move to the next one.